Hi everybody. Today we're going to look at rocket staging. So, what is rocket staging? Rocket staging is the idea that as a rocket progresses throughout its flight, it's burning fuel, and you no longer need to carry the fuel tanks that used to hold that fuel or the rockets that perhaps used to burn that fuel with you, and that as you go, you can jettison off these parts to reduce weight. And as you reduce weight, the rocket engines that are still running then will be able to accelerate you faster because a lower mass means that you'll get more acceleration for the same amount of force. This gives you more delta V, so it's a more efficient way to increase delta V for the same amount of fuel. So the way this works is there's two primary methods. The most common one is to use a separation charge, which is actually just a relatively small explosive in between the two stages. We usually take these and concentrate them on the connection points that hold the stages together, whether that's usually some sort of bolt, actually. This is colloquially known as explosive bolts. So you fire the charge, and it separates all of the charges simultaneously, separate the bolts holding one stage from the other stage. This is the most common one. There is other methods. The most common secondary method is to use some sort of clamping mechanism that holds the two stages together. And then when you're ready to separate, you just simply release the clamping mechanism. I believe this is actually what SpaceX does with some of their rockets. Now, one thing you have to keep in mind is that you're separating physically the structures of the rockets, but you also may have to separate fuel lines if you're feeding fuel from one section to another. You may have to separate hydraulic lines depending where the pumps and lines and actuators are. You may have to separate electrical cabling also. So there's some details here on how it all has to work. So before we go into some of the ideas and advantages of rocket staging, we should probably talk about why you would not want to do it. You're adding complexity to a system. And anytime you add complexity, things can go wrong. All right. We've made more points of failure. What if one of those bolts doesn't separate? What if, a hydraulic line doesn't separate correctly? What if something goes wrong? There's also more cost here. You have to have the mechanisms that actually separate the rockets. And if you have a lower stage of the rocket that has a rocket engine that you're releasing, you're going to need another rocket engine in an upper stage to be able to keep burning the fuel. So you may have to have more parts or separate fuel tanks, which gets more expensive and things like that. So basically, cost and complexity are your big issues here. And remember, complexity often can lead to failure because you just have more things that can go wrong. If you have simple missions that can be done with relatively simple single stage rockets, a lot of times it's not worth it to have stage separation. However, there are some significant advantages. Like we mentioned before, you can more efficiently generate delta V. Now you can use this as a couple of different ways. You can use that delta V just to get the rocket going faster to achieve different orbits and different missions. You can trade off some of that delta V to be able to carry a larger payload, or maybe you just want a smaller rocket, and you can trade off some of that delta V and have less propellant in there and still even out as you would with a single stage rocket. So you can have one or more of those depending on what sort of ratios you want between them. One thing that we would want to note is it's not currently possible with the materials and engineering we have right now to establish a Earth orbit mission without staging. So if you wanted to fly a rocket up into the atmosphere and just take some samples of the upper atmosphere and bring it back, you can do that with a single stage. Or if you were firing a rocket for some sort of military purpose that was going to leave one part of the ground and land on another part of the ground, you can do that with single stage rockets. But if you wanted to get into orbit, it's really hard to do it without staging. So we have a couple of different types of staging. we have what's called serial staging, which is where you basically have two halves of the rocket stacked on top of each other. The rocket fires, and at some point, a lower part of the rocket detaches, and when it detaches, the upper part of the rocket has its own separate rocket engine that takes over and starts firing and burning the fuel in that section. When we go through and look at the math later, this is the only type that we're really going to go into. The math's a little bit easier, and it's simpler to follow. So we're going to focus on that one. I do want to point out that there is a second type of staging. This uses parallel staging, where when the rocket takes off, and you've probably seen something like this with the space shuttle launches, you actually have multiple rocket engines firing. In the space shuttle, you have solid rockets on the sides and a hydrogen burning rocket in the center. And when you hit a certain point, the side booster rockets have exhausted their propellants and they burn out. And at that point, they're discarded off to the side, so you no longer have to carry their mass with you. And the center column continues burning and takes the added velocity exist from the side rockets and then adds on to it. Like I said, we're going to focus on serial staging in this presentation. So let's consider two rockets here. If you remember our rocket equation, the rocket equation, we can calculate delta V by multiplying the exit velocity by the natural log of the initial mass of the rocket divided by the final mass of the rocket. And we're assuming the difference between the initial and final mass of the rocket is the fuel that's burnt. Now, let's consider something that we've done in the past. Let's just look at a one-stage rocket. So in this rocket, we can see, let me go back. We can see up at the top, we've got a small payload here. We'll say the payload is just 1. We're not going to worry about the units here. The structure is 8. There's 80 units of fuel. And we have an engine that, say, has 6 in mass. All right. Fairly common ratios. Now, for our purposes, we're just going to assume for all of our rockets, we have the same exit velocity of 3,000 meters per second. So when we want to calculate this, we add up all of the masses, so 1 plus 8 plus 80 plus 6, and we'll get a total mass, an initial mass of 95. Now, as the rocket burns, it's going to burn all of the fuel. So at the end, the final mass of the rocket, we're going to subtract back out that 80 for fuel. So we go from 95 to 15. So when we calculate our delta V, we'll have 3,000 times the natural log of 95 over 15. And this gives us a total of about 5,540 meters per second of delta V in the rocket. Now, if we have a two-stage rocket, we're going to actually calculate our delta V by stages. So we're going to find how much delta V we get from the first stage, how much can we change the velocity, and then we're going to see how much delta V we can get from the second stage, and we'll add those together to get our total delta V. So let's consider the first stage. Now, one thing we have to remember is that the first stage carries the second stage with it. So the initial mass of the rocket at the beginning of the first stage is everything. So it's the payload, that one mass. It's the fuel from the second stage, the structure from the second stage, the engine from the second stage, and the fuel, structure, and engine from the first stage. It's everything. That's our initial mass. If we add all of that up, we get 97. Now, how much fuel do we actually burn during this first stage burn? Well, if we look on the bottom there where it says first stage, we see the fuel has a mass of 60. So we burn off 60 of the fuel. So we go from 97 to 37. And our delta V is only 2890 meters per second. So not as significant as it was in the first rocket. But here's where it gets a little bit more interesting. So once we've burned off the first stage, we separate it and drop it. Once the first stage drops away, we're left with the second stage. And we can kind of treat this like it's its own independent rocket. So again, we're going to look and we'll say, what was our initial mass? And if we add together the mass, the payload, fuel, structure, and engine, we add them all up, we'll see that it's 25. And we'll say how much of it is fuel? 20 was fuel. So we go from 25 to 5 from the initial mass to final mass. So when we go to calculate this, again, we'll say 3,000 times the natural log of 25 over 5. And we'll find that our delta V for that second stage is 4830 meters per second. Notice neither stage is actually as much as the other rocket was, but when we add them together to get a total delta V, we get 7,720 meters per second, which is significantly more than we had from the first one. So, just to show you that I'm not, doing anything funny with the numbers here, I do want to point out that in these two rockets, both of them had the same payload. They both had a payload of 1. They both had the same structural mass, which was 8. They both had the same total mass of fuel, which was 80. And their overall weights are very similar. The two-stage rocket is actually slightly heavier because it has one more component than the first stage rocket. It has that second rocket engine. So even though the structure and fuel and payload and everything else add up to be the same, that extra rocket engine on the two-stage rocket does make it slightly heavier, actually. So it's about 2.1% heavier. And if we go back and remember the numbers we just looked at, we see the 1 and 2 stage delta V numbers here, and we're comparing 5540 meters per second to 7,720 meters per second. And that's a difference in delta V of almost 40%. So even though we're using the same fuel, same amount of structure, and just slightly more mass to put another engine in there, we're getting almost 40% more delta V by dropping off the unused fuel tank for the last part of the burn with the second stage. So that's the reason we do rocket staging. All right, well, hope you guys are all well. We're going to have a couple homework problems on this later, and feel free to go back and look at this presentation.